about the various power electronic semiconductor devices which are used in the industry. Various types of devices were developed and become commercially available in late 1970s. These devices may be categorized as you can see in the following list. Much of the devices you are much familiar with: power diodes, thyristors, BJTs, bipolar junction transistors, power MOSFETs, IGBTs, and 6 static induction transistors. Well, a brief introduction about these devices. First of all, power diodes, a very simple diode which you have already worked with. Diodes are unidirectional current devices. They can carry the current in one direction. Power diodes are suitable for applications where larger currents and voltages are involved. They have different structures as compared to the ordinary diodes, therefore have a slightly different characteristics. Threshold voltage of power diode is slightly greater than that of the normal diode, that is in the range of 1 to 3 volts. There are three types of power diodes: general purpose, high speed, fast recovery diode, and Schottky diode. General purpose diode is generally not rated for high frequency, whereas the high speed diode are most suitable for high frequency operation, which are normally required for chopper circuits, that is DC to DC converter, whereas the Schottky diode are rated for a very high frequency operation and has a low on state voltage. Thyristors, I have delivered some basic points about the thyristors in my previous lecture. This may be treated as a continuation from that lecture. A thyristor, which is also called as an SCR, silicon control rectifier, it is a conducting device just like a diode, just like a switch. In thyristor, the main difference is that the conduction can be controlled, which cannot be in the case of a diode. A thyristor is a 4-layer device having PN-PN structure with 3 PN junctions. Gate is used to control the delay and the conduction period. These are the respective characteristics which I have explained in my previous lecture. You can go through that previous lecture. These are the different types of thyristors: force commutation thyristor, live commutated thyristor, GTO, gate turn off, reverse conducting thyristor, SIT, static induction thyristor, gate assisted turn off thyristor, light activated SCR, and MOS controlled thyristor. Well, now there is a very important issue about the protection of these power semiconductor devices. Due to the reverse recovery process of power devices and switching actions in the presence of circuit inductances, voltage transient occurs in the converter circuits. Even in the carefully designed circuits, short circuit fault conditions may exist, resulting in an excessive current flow through the devices. The heat produced by the losses in a semiconductor device must be dissipated sufficiently and effectively to operate the device within its upper temperature limit. The reliable operation of a converter would require ensuring that at all times the circuit conditions do not exceed the ratings of the power devices. By providing protection against overvoltage, overcurrent, and overheating. In practice, the power devices are protected from 3 different faults which may occur: dV by dt, di by dt, and thermal runaway. We will discuss briefly about these 3 protections. First of all, dV by dt protection. How can we protect a circuit from dV by dt spikes? Well, snubber circuits are especially used to protect a device from dV by dt spikes. An RC snubber is normally connected across a semiconductor device to limit the dV by dt within the maximum allowable rating. The snubber could be polarized or unpolarized. A forward polarized snubber is suitable when a thyristor or transistor is connected with an anti-parallel diode. Well, due to the reverse recovery time and recovery current, an amount of energy is trapped in the circuit inductances, and as a result, transient voltage appears across the device. In addition to dV by dt protection, the snubber limits the peak transient voltage across the device. The second most important protection is against di by dt. The power converters may develop short circuits or faults, and the resultant fault currents must be cleared quickly. Fast-acting fuses are normally used to protect the semiconductor devices. As the fault current increases, the fuse opens and clears the fault current in a very few milliseconds. The semiconductor devices may be protected by carefully choosing the locations of the fuses. However, the fuse manufacturers recommend placing a fuse in series with each device. When the fault current rises, the fuse temperature also rises, at which the fuse melts and arcs are developed across the fuse. Due to the arc, the impedance of the fuse is increased, thereby reducing the current. However, an arc voltage is formed across the fuse. The generated heat vaporizes the fuse element, resulting in an increased arc length and further reduction of the current. In selecting a fuse, it is very necessary to estimate the fault current and then to satisfy the following requirements. The fuse must carry continuously the device rated current, number 1. The fuse must be able to withstand the voltage after the arc extinction, number 2. And number 3, the peak arc voltage must be less than the peak voltage rating of the device. And the third protection is against the heat. Due to the switching losses and the on state of the device, heat is normally generated within the power devices. This heat must be transferred from the device to a cooling medium to maintain the operating junction temperature within the specified range. Although this heat transfer can be accomplished by conduction, convection or radiation, natural or forced air convection cooling is commonly used in industrial applications. The heat must flow from the device to the case and then to the heat sink in the cooling medium. A wide variety of aluminum heat sinks are commercially available, and they use cooling fins to increase the heat transfer capability. Whereas in high power applications, the devices are more effectively cooled by liquids, normally oil or water. Water cooling is very efficient and approximately 3 times more effective than oil cooling. However, it is necessary to use distilled water to minimize corrosion and antifreeze to avoid freezing. Oil is flammable. Oil cooling, which may be restricted to some applications, provides good insulation and eliminates the problems of corrosion and freezing. Heat pipes and liquid-cooled heat sinks are also commercially available. Thank you, students.